Now we look at examples of the disk and the washer method. So in these exercises, we're going to find the volumes of the solids generated by revolving the regions bounded by the graphs of the equations about the given lines. So these are our three equations, and we are going to revolve the region bounded by them. First about the y-axis, then about the x-axis, then about the line y equals 8, then about the line x equals 2. So let's go ahead and take a look at the graph. This graph came from the TI-83 Plus calculator. I just put in y equals 2x squared. It gave us the graph of this parabola right here. So this parabolic or quadratic graph is the graph y equals 2x squared. And the line y equals 0 is actually the x-axis down here. And the line x equals 2, well, you notice x starts 0, 1, 2. So the end of this graph over here, the right-hand side, would be the line x equals 2. And the region bounded by those three graphs is the region underneath the parabola above the x-axis and to the left of the line x equals 2. So it's this region that I'm shading red here. This region here is the region that we are going to revolve about all those lines and create solids. Now, depending on which one of those lines we revolve it about, we're going to get a different shape. But this is the plane region. And what we're going to do is we're going to come up with representative rectangles to represent the different plane regions that are going to be revolved around these different lines. But this is the plane region that they are speaking of that we're going to revolve around an axis of revolution. So first, we'll rotate about the y-axis. And the y-axis is this axis over here. So we're going to rotate about this axis. And that's a vertical axis. Now, the other thing that you should notice is that there is actually some space right here between the plane region and the axis of revolution. Whenever there is a space between the plane region, which is this red shaded region over here, and the axis of revolution, which is the y-axis, we have to employ the washer method. So we're going to use the washer method, and the first thing we want to do is we want to draw a representative rectangle for our plane region. So I'm going to draw a rectangle, and this rectangle, when I create a disk from it, the disk is going to have a radius that is perpendicular to the axis of revolution. So once I revolve this rectangle around the y-axis, the radius of the disk created is going to be perpendicular to the y-axis. And that's why I draw the rectangle this way. Now, if you notice, this creates two different radii. One of them, a smaller one, that goes from the axis of revolution and it goes all the way over to the function. We're going to call that the little r of, in this case, y, because we're going to be doing our integral with respect to y because we're integrating with respect to the y-axis. We actually have to modify this formula a little bit. Now, the other one is the big R of x, which is the distance from the axis of revolution all the way to what would be the top of the disk, which is up here. And that would be the big R of x, that, or in this case, R of y. So that would be the big R of y. So we have two radii now. And we just need to come up with the description of those two with respect to y. Basically, we have to modify this formula a little bit because our axis of revolution is a vertical line. So instead of integrating from a to b, where a and b are both y values, we're going to integrate this thing with respect to x. So it's going to be the capital R of y squared instead of the capital R of x. So this is going to be squared minus the lowercase r of y squared, r of y squared. And instead of dx, we're going to have dy, because the width of this rectangle is actually a small change in y, delta y, which we are going to call the little differential dy. So we're going to modify our equation a little bit because of the fact that we have we're going to be using functions of y because the axis of revolution is vertical. So it turns out that the r of y, well, the r of y is the functional value if you look at this parabola as a function of y instead of a function of x. So if you solve this equation to make x a function of y as opposed to y a function of x, you would divide both sides by 2. So you start off y equals 2x squared. You divide both sides by 2, you get y over 2 is equal to x squared. And then you take the square root of both sides, you get the square root of y over 2 is equal to x. So this is that function of y that we were talking about. This is the lowercase r of y. It's this parabola in terms of y instead of in terms of x. So we've gotten one of our measures already. We know that the r of y that we need, the r of y, oops, not f, we know that the lowercase r of y, the lowercase r of y is equal to the square root of y over 2. So we have this for our r of y. Now, the capital R of y is a constant height. If you notice, no matter which rectangle you draw, the top of the rectangle or the extreme right of the rectangle is always at this vertical line here, and this vertical line is the vertical line x equals 4, which is just 4. So we know that the capital R of x, the capital R of x, capital R, or not of x, but of y, we know that the capital R of y is equal to just the number 4. It's a constant function of y, and it's always equal to a value of 4. So now I have my lowercase r of y, my uppercase r of y, and I know that dy is just the width of the individual representative rectangles, and we're integrating y from a to b. So we're integrating y from a to b. Well, it seems like this shaded plane region that's shaded in red here starts at a y value of 0, so that a is 0, and it ends at a y value of 8, so that b is 8. So now I know the integral that I need to set up. So let's go ahead and set up the integral. So the volume of the solid of revolution is going to be pi, and I'm going to integrate from a to b, which we just discussed. The y values start at 0 and end at 8. And I'm integrating with respect to y, so I know I have to look at the y-axis for my lower and upper limits of integration. The capital R of y, the capital R of y is the number 4. So I'm going to get here 4 squared, and then minus the lowercase r of y. Well, the lowercase r of y is the square root of y over 2 squared. And then I'm integrating this with respect to y. So there I have the integral that I have to evaluate in order to get the volume of this region. Well, let's see. Let's do some calculation over here so we know what all these things are. So what we have here, we have our integral set up. Let's see if we can simplify it a little bit. So we get here that the volume is actually equal to pi times the integral from 0 to 8, and then 4 squared is 16 minus, well, if you square the square root of y over 2, then you just get y over 2 dy. And this is the integral that is going to give us the volume of the surface or the solid of revolution. And it's a relatively simple integral actually, based on how we had to derive it. Well, let's see, our integral yields, oops, let's get our pencil back. Our integral yields pi, and then when we integrate 16, we get 16y, and when we integrate y over 2, we get y squared over 4, and we are taking this from 0 to 8. So we get, this is pi, and then 16 times 8 is 128, minus, well, this is 8 squared is 64. 64 over 4 is 16. And then when I do this subtraction, I get that the volume of the area, or the volume of the solid of revolution is going to be 128 minus 16, which is 112 pi. Okay, part B is to revolve about the x-axis. So we're revolving about this axis now. So when we draw our representative rectangle in this case is going to be the radius of the disk that it would create should be perpendicular to the x-axis. So the representative rectangle is actually going to be vertical like this. And in this case, we are going to be integrating with respect to x, because we see this distance here, that's our little delta x, a little change in x, which is what we're going to call dx, which is going to be the width of our disk. Now, in this case, I also want you to notice that the plane region goes right up to the axis of revolution. Unlike the last example where there was a space between our plane region and our axis of revolution, in this case, the plane region is flush up against the axis of revolution. So we don't have to use the washer method. We can use the disk method, and there's only going to be the one radius, capital R. So capital R is going to be this height right here. And in this case, we want that to be a function of x because we're integrating with respect to x. All right, so this is going to be the model. R of x, well, R of x is the height. And the height here as a function of x is the same height we've been looking at. This is the line y is equal to 2x squared. We don't have to modify it to make it a function of y. It's already a function of x, and we're integrating with respect to x. So plugging all of this information. Oh, the other thing that I need to note is that unlike y, which ran from 0 to 8, in this case we have x, which is only going from 0 to 2. So in this case, a and b are also different. The limits of integration are no longer y values, so I'm not looking at the y-axis for my limits of integration. They're now x values, so I'm looking at the x-axis for my limits of integration. And this is going to be the integral from a to b, which are actually x values. The plane region starts at 0 and goes all the way up to 2 on the x-axis. So this integral is from 0 to 2 of the r of x squared. Well, the r of x in this case is just the height of this representative rectangle, which is actually the functional value, the y value if you plug in an x value, which in this case is only 2x squared. It's the original parabola there. So the r of x is 2x squared, and we're just going to plug that in here. So it's going to be 2x squared squared dx. So this is the integral that I am going to calculate to give myself the volume of this shaded region. So let's go ahead and do that integral. Let's see. This is the integral from 0 to 2 of 4x to the fourth power, it would seem. 4x to the fourth power dx. And I believe this gives us 4 fifths, 4 fifths, x to the fifth power going from 0 to 2. And then all we have to do is plug in our upper and lower limits. Oops, oops. It seems like in the calculation I've been forgetting to bring along the pi. Can't forget the pi. Used to make that mistake when I was an undergrad too. So pi comes here also. And here's a pi over here also. So what we get is when we plug in these limits of integration, we get 128 pi over 5. And that would be the area of that region. Or excuse me, not the area of that region, the volume of that region. Okay, now we look at the volume of the solid generated by revolving this region about the line y equals 8. Well, the line y equals 8 is a horizontal line. It's this line right here, and we're going to revolve about that line. And when we draw our representative rectangles, then remember, we want to draw a representative rectangle in a way that makes the disk that is going to generate have a radius that is perpendicular to our axis of revolution. So basically, we're going to draw our representative rectangle vertically this way, since our axis of revolution is horizontal. Notice again here that there's a gap or a space between our representative rectangle that represents the plane region and the axis of revolution, which is the line y equals 8. Well, that gap means that we have to use the washer method, and we're going to have an inner radius, lowercase r, of x in this case, because we are integrating with respect to x. Our representative rectangles are going horizontally across to represent this entire region. So we're integrating with respect to x. The inner radius, the lowercase r of x, is going to be this distance right here, lowercase r of x in this case. And the other one is going to be this distance right here. That radius is going to be the uppercase r of x. And we just have to figure out how to describe both of those radii. All right? Well, let us see here. The first thing is the smaller radius, the one I have in green here, lowercase r of x. Well, that smaller radius is actually the difference between 8 and the value of the function. You see, the value of the function is everything from the x-axis up to the function itself. The difference between that number right here and 8 is actually how long my inner radius is. So the lowercase r of x is actually equal to 8 minus the value of the function, and the value of the function is 2x squared. So that's my lowercase r of x. My uppercase r of x, this one here, the uppercase r of x. Well, the uppercase r of x is always the same number. It's the distance from the axis of revolution to the x-axis. So the uppercase r of x is actually the number 8. It's always 8 units long. No matter where you are, the rectangle will have a distance, the far part of the rectangle will have a distance of 8 from the axis of revolution. So this is my lowercase r of x, this is my uppercase r of x, and the only thing I need to do is now find a and b. Well, since we're integrating with respect to x, we're using dx, a and b are going to be the x value where the region starts, that's going to be a, So a is equal to 0, and the x value at which the region ends, and that x value is 2. So b is equal to 2. So with this information, we can actually set up the integral that will give us our volume for this solid of revolution. So the volume is going to be pi times a, the integral from a to b, which is from 0 to 2 of, let's see, we'll put a bracket, and the uppercase r of x is 8. So that's 8 squared minus the lowercase r of x is 8 minus 2x squared, 2x squared, and this is also squared, and I close the bracket, dx. So this integral will allow me to find the volume of this region. And this integral simplifies to pi times the integral from 0 to 2 of 32 x squared minus 4x to the fourth dx, which is equal to pi times 32 over 3, 32 over 3 x to the third power minus 4 over 5 x to the fifth, and this is from 0 to 2. Upon plugging in our upper and lower limits of integration, we get that this integral is equal to 896 over 15 pi, and that would be the volume of the solid of revolution. Okay, and the last one is the solid that will be generated by revolving our region about the line x equals 2. Well, this is the line x equals 2, and we want to look at the solid generated by revolving about that line. Well, the first thing I want to do here is I want to draw a rectangle to represent this region, and I want that rectangle to produce disks that have radius that have radii that are perpendicular to the axis of revolution. So I'm basically drawing a horizontal uh, representative rectangle because my axis of revolution is vertical. So here is my representative rectangle. And the representative rectangle, well, the width of that representative rectangle is delta y, or dy. And now I just need to look at the radius. Well, because it goes right up, the region goes right up to the axis of revolution, I can use the disk method, and that only requires me to define one radius, and that radius is the distance from the axis of revolution to the top of the representative rectangle. I'm going to call that r of y. It has to be a function of y, as you see when we have a vertical axis of revolution. So we get that r of y because we know that this function is y equals 2x squared. And like before, we solve this for x to make it into a function of y. So we divide by 2, and then we take the square root to get x is equal to the square root of y over 2. So this is our r of y. Our r of y is equal to the square root of y over 2. So basically, when I do this integral, it's going to be in terms of y. So my limits of integration, a and, or I guess C and D in this case. C and D are going to have to be um, values of y. So as I look at this, it seems like my plane region starts at a y value of 0, so that would be the lower limit of integration, and goes all the way up to a y value of 8. That would be the upper limit of integration. And now I can set up an integral to represent the volume of the solid generated. So let's go ahead and set up the integral with all this information here. Well, let's see. We have that the volume of the solid is going to equal pi times the integral from c to d, which is 0 to 8. And this is going to be the r of y, which is this function up here, the square root of y over 2 squared. So I'm raising this whole thing to the second power dy. And this integral will give me my volume. So cleaning this integral up a little bit, we get that this volume is equal to pi times the integral from 0 to 8 of y over 2 dy, which is equal to pi times uh, y squared over 4 evaluated from a lower limit of 0 to an upper limit of 8. And upon plugging in the limits of integration, we get that this is equal to 16 pi.